All right, so here we are back again with some example problems to practice the idea of definite integrals that we are currently learning. So this is going to run very similarly to the indefinite integrals that we've been working so diligently on in the past, but we have a few extra steps to really get us here, at least through these examples, to some numerical values that these integrals will result in. Our series will actually continue forth with a lot of other types of integrals which might not even give us numerical answers, but still is very important for us to analyze what these integrals are doing, and such will be helpful for us on the AP exam. And so before we begin, again, there are a couple of updates in which I will continue to spout forth. Of course, first off, you can go ahead and email me right here on anything you have directly asking about any sort of questions or things you want me to make a video on, and we can get along that pretty quickly. And then today, being actually Tuesday of the time of this recording, is that I will be again here online from on our live stream from 4 to 7 p.m. Pacific time, and there I'll be going over a full AP Calculus packet of an old exam free response questions, but anyone can come in and send in their questions right live, and we should be able to go and answer that just right then and there. Okay, so with that, we should be able to get started with these problems. So why don't we begin? So to begin with, we have the integral. Now remember, we are reading the limits from bottom to top. So again, this is the integral from pi over 3 to pi over 2 of the function tangent of theta over 2 and secant squared of theta over 2 times d theta. Okay, so we have quite a few things here to take note of course. Well, at least for one, our note here is that this looks very oddly similar to what we're dealing with here. Is can we obviously get here from tangent times secant squared? Well, we do have a rule for that, if you remember from our indefinite integral series, is that getting from tangent times secant is quite easy, at least on one regard, is that we're going to have the tangent of x times the secant of x of that function dx. Okay, so you can take an integral of something like this, and then that will result in the actual form of just secant of x plus c. And this is the indefinite form, but of course something to note is that this secant is to the first power, but this secant squared is obviously to the second power, right? So what can be done here about this? Because this doesn't necessarily immediately translate over to something like this. Surprisingly, we actually have gone over something like this before as well previously, but something, if we want to really make sure that we are on this right track, of course, is we can then understand that secant squared of x, if we took that derivative, okay, so let's try to think about this in a little bit more of a backward sense here, is that we will then result in a 2 coming down thanks to the power rule of derivatives. So it's be multiplied by secant of x, and then we still actually need to multiply by secant of x's derivative, which thankfully we already have written out in the integral form back there. And so the actual derivative of secant of x is going to be secant times tangent of x. And when you look at that, we've actually grouped it all together of having these two combining, because they're all being multiplied together, which then this will clean up if we were to finish our thought here of 2 times the secant squared of x times tangent of x. Okay, so not so bad. For what we have here just as some side scratch work for us, just to get our mind up and running about what is currently going on in these types of problems. But with that, looks like we have something that is on the right track to match exactly what we have on this end. Of course, we were using a different variable of theta, and we have that over 2 to deal with, but let's go give this a go just to get our minds on the right track on this. So let's start first with the secant squared of theta over 2, right? If we were to use this as our proposed result of our integral here, right, what would we result with, right? From theta over 2, again, looks like something convenient does happen here, is because we know that, we'll remember that the 2 will come down thanks to power rule. So that we can draw this to the side here. As a coefficient-wise, we're going to be multiplying a positive 2 thanks to power rule, but also thanks to chain rule, we have the theta over 2, which that must be having its derivative taken as well afterwards. So that results in a 2 multiplied by a 1/2 that we know is going to happen if we were to check this work. And when you look at that, those cancel into a nice even 1. And so, looks like there's no other extra coefficients we need to throw onto here. And looks like secant squared is really just the actual result of the indefinite integral for this. But we still have to make sure that we are defining that we are going to evaluate the limits on this problem. All right, we can't add a plus c because we know exactly where these limits of the function are. So let's make sure we add that in. So pi over 3 is the first limit, and then pi over 2 is the ending limit. All right, and so this will result as to the next step of our problem here. Okay, and would you look at that? We actually did this problem quite quickly, even though this is a definite integral. But thankfully, thanks to all of our experience with indefinite integrals, we're able to get to this part pretty easily. Now comes the actual unique part of this, of course, which is going to be defining and analyzing the limits of this kind of problem. Okay, so with secant squared, let's go and now go from, remember from fundamental theorem of calculus, is that it is the first limit minus the second limit for this new function. So it's going to be pi over 2 over 2. So that's the first limit that is taken care of. And then we need to subtract it with secant squared of the second limit, pi over 3 over 2 in that function. Okay, we're continuing our pace along here. So let's just clean up what's inside of each of these guys. So it's going to be pi over 4 inside the first secant squared, and then it's going to be pi over 6 in the second secant squared. Okay, so for those who might have trouble with understanding or trying to draw a connection to the reciprocal trig functions, looks like all we need to do is take a second note here, is that we have, let's go first with cosine, and then we just flip it over on the reciprocal. So cosine of pi over 2, or 4 that is, sorry. Cosine of pi over 4 matching what we have first. Again, drawing from great vast knowledge of the unit circle is going to be rad 2 over 2. And then the cosine of the pi over 6. Once more, if you remember exactly where that pi over 6 is on the unit circle, means that we are actually closer to the 1 than further away from it. So that means it's rad 3 over 2. Okay, and so now we just need to flip them over for the sake of secant here. And so by flipping them over, we will then understand that we are going to get rad 2 as the result, and then we'll also get, in this case, if we were to think about how we can come up with the simpler version, is that you'd flip it over first at 2 over rad 3, and then we need to rationalize this fraction there. So it's rad 3 over 3 on each other. So it's going to be 2 rad 3 over 3 is the result of the next one. Okay, so those are what we have right now. Okay, and so with that, we can then substitute all that in there. So it's going to be rad 2, all of that squared, minus, then from the other side is going to be the 2 rad 3 over 3, all of that squared. Okay, and so we end up with a 2 minus, now from the second guy squared there, is going to be a 4 times 3 all over 9. Okay, which again, running through some very simple algebra here, is that this 3 can cancel with that 9, making it the denominator 3, so it's 4/3. Okay, and so some last steps here is that the 2 will then simplify to 6 over 6 minus a 4/3, which will then give us a 2/3 as a result, finally, after all of this work. Okay, so there was quite a few steps just algebra-wise and pre-calculus-wise and all that stuff, just to make sure we're on the right idea for these types of trig functions. But the main steps here are going to be to actually remember that we still need to run the actual indefinite integral. Make sure that we plant in there that we will still evaluate the limits. And I think up to this part is really the main purpose of why we're doing these types of problems, is to know how we can plug that in and then evaluate using all prior knowledge. Okay, so a little bit of a longer section here, but still, I think we're good for the type of practice that this problem brings. Let's get to another one, and we'll see where that one takes us. And so here we are at our second problem, something a little bit more straightforward with just the integral now evaluated from -1 to +1 for the radical of 3x plus 4. And so our rules still apply about what we're doing so far, but just to make sure we're on the same page here is that the -1 and 0 is the correct order of this. Again, we are reading it from bottom to top of usually the lesser number, then -1 ending at the greater number of 0. Okay, and so because we have this root here, we're going to have to go make sure we have the right note here, given that we are dealing with 3x plus 4 raised to the 1/2 power, right? That is the result of having that in the square root. Okay, so if we were to go and take that kind of integral, we will need to make sure that we are using 3x plus 4 now raised to the 3/2 power. Okay, pretty straightforward there, but of course that we need to make sure that because we're raising to 3/2 power, and if we're going to go and check that work, we need to make sure that we slap on a 2/3 coefficient to match and remove that 3/2 coefficient coming down, which is now part of that problem. Okay, and so one last thing to note, of course, is that thanks to chain rule resulting from this type of derivative, if we were to check back the answer, we will then result in a fat 3 coefficient waiting for us once that problem is through. Okay, so we've taken care of the fact that we dealt with the exponent's coefficient, and now we need to deal with the fact that inside of the square root, we're going to have another coefficient emerging after the derivative. And so because of that, we need to make sure you multiply another 1/3 to counteract that full 3 coming out. Okay, so why don't we just clean this up here, and so we can make sure we have everything in order. So our new coefficient will be 2/9 this time of 3x plus 4 all raised to the 3/2 power, and then we will then evaluate the limits. Remember, that is an important step to make sure we don't finish the problem with plus c and getting everything wrong here. So let's actually input the limits here from -1 to 0 for this problem. Okay, so as always, this should all be second nature to us after us studying so hard about those indefinite integrals. And now we're getting to the new territory of evaluating these limits. Okay, so what we could do, thankfully, is that similarly to the coefficient rule of indefinite integrals, we can leave that 2/9 outside, just waiting very calmly for the rest of these guys to figure out what those limits are. Okay, so 3x plus 4, let's evaluate the top limit first. So it's going to be 0 plus 4 raised to the 3/2 power. And then we subtract it with the lower limit now, which is going to be 3 times the -1 plus 4 still raised to the 3/2 power. Okay, there we go. And so with that 2/9 will wait there. And now, so we have 4 to the 3/2 power. Okay, so just to take a note here is that 4 to 3/2 power means that it's then instead, because 4 can actually be taken to the square root quite easily, that is going to be instead 2 to the 3rd power, which for us is going to be just a +8 as a result from that. And then that'll be a -3 plus 4, which will be a +1 to the 3/2 power, which a +1 to the 3/2 power, well, in any case though, is just going to be 1. Okay, looks like we are well on our way to discovering what this last bit will become. So we have a 2 over 9 multiplied by 8 minus a 1. Thankfully, after these exponents are pretty easy to solve with. So it's going to be 2 over 9 multiplied by a positive 7 over there. Okay. And then we just multiply across in the numerator, making it 14 over 9. There is nothing else left to simplify off of that. And so it turns out this integral does give us a numeric value of 14 over 9, evaluated from -1 to 0. Okay. So again, this is meant to be fairly straightforward just to begin with. We are simply taking our indefinite integral knowledge just to an additional step here. And so with that, we should be able to then build off of understanding what exactly these definite integrals will look like on a graph. Oh, yes indeed. We will have graphs and we will start doing areas underneath the curve, starting with some approximations and then into some real good business for us just to be able to answer a lot more questions that are coming up on the exam. So we'll be back here tomorrow with the next lecture in this series. But as a reminder, again, we are streaming tonight, given that this is a Tuesday, from 4 to 7 p.m. Pacific time. And you can come by and ask all your questions live if you have any, or you can follow along with the free response questions of, I think this time will be the 2014 AP Calculus AB free response questions. So with that, we should be able to go ahead and start putting that together. All right, so thank you all for watching once more, and we'll see you in the next one.